Hello again, everyone. Welcome back to another episode. This is going to be a pretty exciting one. We're finally going to get something on the screen after, 11 videos. So it's going to end up being a bit of a long episode, but I just really want to get to this point because it's frustrating going through episode after episode without actually having anything physical to show for it. So the last episode we finished creating the graphics pipeline, so in this episode we can move on to creating frame buffers and command buffers and then finally set up the rendering. So let's go ahead and get going. First off, we will create frame buffers for the input and output of the graphics pipeline. So we're going to need to create a vector of frame buffers in the header file, and they're all going to need to be wrapped with vDeleter because that's just kind of how things go. So right here. Alright, so we do another vDeleter. And these are going to be sorry, not vDeleter. It's a vector, like I said. So we actually do a std vector. It's going to be a vector of vDeleter objects. And all of those are going to be wrapping VK-FrameBuffers. Just like that. And we'll just go ahead and call this swap chain frame buffers. There we go. Perfect. So now that we have that, we need to actually create these frame buffers. So we're going to make a new function for that. We're just going to call it createFrameBuffers. We'll drop that in right after create shader module. That looks like a good spot for it. So we just do void and create frame buffers. Alright. And why don't we just take that, we're going to bring it over into the CPP, and we want to call that right after we create the pipeline. So we'll just drop that right there. And we're going to head down. We did after create graphics pipeline, so we'll just do drop down here. That's not it. Where did it go? There we go. Found it. So right after that, actually, you know what? Let's put it. Sorry about this bouncing around. We should put it after create shader module because that's referenced in the graphics pipeline. So create frame buffers right here. Void planet Vulcan create frame buffers. Perfect. That looks nice. Alright, so since we want the frame buffers that we're creating, each individual frame buffer is going to be associated with a swap chain image view that's in the other vector. So we need to actually go through the previous vector and then associate each one of those with a new frame buffer. So what we're going to do is we're going to say swap chain frame buffers, and we need to resize that so it's the same size as the swap chain image view vector. So swap chain image views dot size. So now we should have equal sized vectors. And we also, since we're going to all of those swap chain frame buffers that we had, if you remember, they're vDeleters, so we need to actually initialize them. So we're also going to put right here vDeleter VK-FrameBuffer, and we're going to pass in the logical device like usual, and then the destroy function for it, which is going to be VK destroy, not destory, destroy, and frame buffers, or frame buffer, singular. Alright, there we go. So now our vector of swap chain frame buffers is going to be the size that we want, but there's nothing really being done with those, so we need to go ahead and call a create function on each one of those frame buffers. So we're going to need to make a for loop. So for, and we're going to do size t I equals 0, and then as long as I is less than swap chain image views dot size and increment I. Alright, so what we're going to do in here, we're going to go ahead and call that create function like I said. So it's just going to be if, and this is the same format we've been through a million times, create vk create frame buffer, and we just pass in all the usual arguments. So it's the logical device, then a frame buffer info, which we're going to have to go back and fill out. So we'll just call it, we'll call it frame buff. Wow, can't type today. Frame buffer info. There we go. And a null pointer for the p allocator. And then swap chain frame buffers. And this is going to be the particular frame buffer at this index. And we're going to call replace on it. And as always, we're going to check whether or not that equals VK success. And we're going to go ahead and throw an error if it doesn't, like usual. But we're not going to put out any sort of success inside the for loop, because if we did, we'd have a massive wall of success messages, and that wouldn't really help us out very much. So throw runtime error, and we'll say failed to create frame buffer. There we go. And just to make sure everything turns out all right outside of the for loop, we're going to go ahead and say std cout, and we'll say frame buffers created successfully. All right. Oh, and we want to end the line. There we go. So now if this succeeds, it'll only read that out once. We don't want to get a whole wall of stuff. But we need to fill out that frame buffer info. So we'll hop right back up here. And it's going to be vk frame buffer. Oh, I'm sorry, no, vk frame buffer create info. We'll call it frame buffer info, just like we did below. There we are. And we need to fill out all the data, so frame buffer info s type is going to be vk structure type frame buffer. There it is, frame buffer create info. I'm sure everyone could have figured that out on their own. So frame buffer info, we're going to do render pass. Oh, I got caps lock on, that's not good. And we're just going to set this equal to the render pass that we already set up. There we go. And next up, we have FrameBufferInfo.attachments, or attachment count rather. We're going to need to give it a count and then the attachments to pass in. The attachments we actually haven't declared yet. We have them though. We're just attaching each one of these frame buffers to one of the swap chain images, just like I said. So what we're going to do is right up above here, we're going to go ahead and add in a VK image view. There we go. We'll call it attachments, just for simplicity. It's an array. And we're going to go ahead and pass in swap chain image views, and it's whichever one we're at the index of. So we did create an array, but we're only passing in one object in the array each time. It just has to be an array. That's what it's expecting in terms of format. And I believe I need a semicolon. There we are. Perfect. So now we have attachments. The attachment count is only one because there's only one object in there that'll get you the first index. And then we're going to do FrameBufferInfo.pAttachments and pass in a reference to the attachment array, which is just attachments. All right, now we also need a width and a height, so FrameBufferInfo.width equals swap chain extent dot width. Everything matches up nicely with the swap chain stuff that we made already. FrameBufferInfo height equals swap chain extent height. There we go. And we also need layers. So FrameBufferInfo layers. And there's only one layer because we're not doing anything with multiple layers. So that is everything we need to create the frame buffers. So now we can move on to sending commands to the pipeline. So to call commands in Vulkan, you have to set up anything you might want to do in command buffer objects. And before we do that, we need what's called a command pool to handle the memory that the command buffers use. So we need to make a new Vulkan object in the header file, and just plop it right here. This is going to be well, first it has to be wrapped in a vdeleter, and it's going to be a vk command pool. Everything is named what you would expect. We'll call it command pool. There we go, command pool. And as usual, we need to give it logical device and its delete function, which is going to be vk destroy command pool. Perfect. Okay. Right after that, we're going to need to create a function to create the command pool. So right up here, under createFrameBuffers, we're going to do void create command pool. And we're just going to grab that. There we go. Pop over to the CPP and go back up to the top. And right after create frame buffers, we're going to create the command pool. And then let's drop back down to where we were. Oh, no. Let's just keep on going back. There we go. And so right after create frame buffers, we're just going to add this in. So void planet Vulcan, and there's our function. So once again, we're going to make another create function. So if vk create command pool does not equal vk success, and we'll give it brackets first. Let's fill that out, and of course it's logical device. Then another info that we haven't filled out yet, we'll call it pool info. Null pointer for the p allocator, and then command pool dot replace. Nice and straightforward right there. And we'll go ahead and fill all this out right now. So std runtime error failed to create command pool, and then else cout command pool created successfully. Great, so let's fill out that pool info real quick. We're going to declare a vk command pool create info. Call it pool info. Alright, and now we fill out all the data, so we need a pool info s type, and that's going to be a vk structure type command pool. There it is, command pool create info. And we also need a pool info q family index. And if you remember a few episodes back, we set up that q family index structure over in the header file. Where is it? Here we go, q family indices. So we're just going to use that. It's going to make things a lot simpler. So right up above it, we're going to retrieve that. We're just going to say q family indices. We'll call it q family indices. There we go. Oh, spelled that wrong. Indices. And equals find q families. And we pass in the physical device to locate that. And now that we have those indices, we can just go down here to QFamilyIndex and assign that to QFamilyIndices.displayFamily. And that will get us everything we need. And in case you're wondering why we're using the QFamily indices here at all, we submit commands on the queue. That's why we located it in the first place. And since we want to submit display commands, we found a queue that handled display commands. So that's the one that we're going to be using here. So now that we have this is everything we need for our command pool, we can go ahead and start creating the command buffers. Each buffer is going to need a reference to the current frame buffer, so we need to make a command buffer for every image in the swap chain, kind of like we did before with the frame buffers. So we're going to go right back down here after the command pool, and we are going to create command buffers. So it's going to be another vector. It's std vector, and it's going to be vector of vk command buffer. And the nice thing is we actually don't need a v-deleter wrapper for the command buffers because those are cleaned up internally. So we're just going to call this command buffers. There we go. And just like everything else, we're going to need a function to create these as well. So pop right back up here. After create command pool, we'll do void create command buffers. Bring that over to the CPP. Actually, since we're right down here, I'm just going to drop it down here first, because I'm going to need to come back here in a second anyway. Alright, so there's our function. Let's jump back up to the top real quick, stick it in there so we don't forget to call it, and we'll jump back down. So the setup for the command buffers is going to be similar to what we did with the frame buffers. Since we have a vector of them, we need to resize it so that we have one command buffer for every frame buffer that we declared. So it's going to be command buffers, resize, and we're going to go ahead and pass in swap chain frame buffers dot size. There we go. Alright, so now that we have that, we need to create the command buffers, but it's not a standard create call. It's actually an allocate call. So what it's going to be here is we're going to say if, and it's vk allocate command buffers, and once again we're going to double check if that equals vk success, and we're going to pass in, it's mostly the usual stuff, just logical device. You still need to create info, even though this isn't a standard create, and we're going to say alloc info, and then command buffers data. It's actually expecting a vector of command buffers, so this vk allocate call, we're not going to need to call that on every single one individually, because as you'll see in just a second when we fill out the info for it, the allocation info, it's going to specify how many buffers we have. So let's go ahead and fill that out now. Before we do that, actually, let's go ahead and do our error. So std runtime error, failed to create command buffers, and then else having some trouble typing. Command buffers created successfully. There we go. std endl. Great. So real quick, we're going to fill out that alloc info. It's just going to be a vk command buffer allocate info. Call it alloc info. The structure is very similar to a create info. There's not much difference to it at all. Do alloc info dot type equals, and this is going to be a vk structure type command buffer allocate info. And then we pass in the command pool that we needed to create before. So it's a good thing we already did that. Command pool equals command pool. And then alloc_info, no, it needs to be spelled right, .level. And this is going to be vk command buffer level primary. So all that means is that the command buffer can submit commands directly to the queue. We don't need that open anymore. And then the last bit of data is alloc_info. It's alloc_info command buffer count, like I said. And we're just going to pass in, we're going to cast it as a uint 32t, and it's going to be command buffers dot size. So now it knows how many to allocate. So now we have everything we need to allocate the command buffers properly. We can start actually writing commands to them. The thing is, with the command buffers, you actually have to start recording on the buffer, call commands, and then end the recording. So we're going to have to iterate through every single one of these command buffers and do that process over and over. So it's time for another for loop. So we're just going to drop down here. We're going to say for. Let's give it its brackets. Don't need that. There we go. For. And it's going to be size t, I equals 0, I is less than command buffers dot size, and increment I. Alright, so what we're going to do, to start the recording, you have to call vk begin command buffer. So it's just vk begin command buffer. And you have to pass in the command buffer you want to reference, which in this case is going to be whichever one we're on the index of. And you also need to pass in a begin info, which again is sort of like a create info. It's really not that different. So we're just going to pass in one that we haven't declared yet, and let's declare it. So we hop right up here. It's going to be a vk command buffer begin info. Call it begin info. And we got to pass in all the data. There's really not that much. It's not too bad. There's an S type, as always, which is going to be vk structure type command buffer begin info. We need a begin info flag, which in this case is going to be vk command usage. Oops, sorry, command buffer usage. Hit the caps lock again. Simultaneous use bit. That's the one that we want. Simultaneous use bit just means that it'll allow us to write to a command buffer even if it is still waiting to execute, so it won't lock anything down. Alright, so we've got all of what we need for the begin info here. We're calling begin command buffer, which means that we can start writing to it. So let's just drop down right beneath that and move on. So right underneath this, we're going to set up the commands for drawing. So first we need to start with a render pass. This is done by calling vk cmd begin render pass. There we go, just like that. And we're going to pass in the current command buffer, so command buffers I. We're also going to have to pass in another info. In this case, it's a render pass info, so we'll just call it that. Keep things simple. And we also need to pass in, you'll see it right here, it's a vk subpass contents. And we're going to set that to vk subpass contents inline. That's the one that we're going to want here. That just means that all the commands will come from this command buffer directly and not from a secondary buffer. So, like I said, we need that render pass info, so let's go ahead and make a spot for that. We're going to go ahead and declare a vk render pass begin info. We'll call that render pass info. So hopefully it should stop yelling at me. There we go. And we're going to need to pass in all the usual stuff, the S type, which is vk structure type render pass begin info. There it is. And we're also going to need a render pass info dot render pass, which is just going to associate with the render pass that we created before. And then we also need the frame buffer, which we also already took care of, just frame buffer equals, and it's going to be the swap chain frame buffer at the exact same index as the current command buffer. It all makes sense. Now there's a little bit more data we need here. We need a render pass info, and it is a render area. And there's actually a few details to the render area. There's an offset, and we're just going to make that be 0, 0. We don't want an offset. That would be silly. At least for our purposes. There we are. And we want the render area to be the same as the swap chain image. So for render pass info render area dot extent, we're just going to pass in the extent we already have. Swap chain extent. Keep things as simple as possible. Alright, the last bit of data we're going to need is a clear value. So the thing is, we need a clear color for when we load the color attachment, whenever it wipes everything. So we're going to define a new vk clear value. There, clear value. Alright, and we're going to call this clear color. And we're just going to set it to black. So it's going to be 0, 0, 0, 0, 0.0, and we want 1.0 for the alpha because we want it fully opaque. We're going to go in the render pass info. It needs a clear value count. We only have one because we just created it right there. And then we need to pass in the pointer to the clear values, which is going to be, a reference to clear color. Just like so. So that'll just tell the render pass how to clear on a new pass. So this handles everything we need for the render pass command. Now we need to set up a command to bind the graphics pipeline. So right underneath begin render pass here, we're going to make a vk cmd. I'm not seeing it there. vk cmd bind pipeline. There it is. And we're going to pass in the command buffer that we're currently referencing. I keep doing that. There we go. Command buffer. We're also going to pass in, for the second parameter, it wants a vk pipeline bind point. And that's going to be vk pipeline bind point graphics. That's the one that we want. And that just tells us that this is a graphics pipeline. And then we need to pass in a reference to the pipeline. And if you remember, the pipeline is just graphics pipeline. We made it earlier. All the things we made earlier are coming back around. So now it's time to finally get to the draw command. And this is actually pretty simple. We're going to pass in, well, first we're going to declare vk cmd draw. Just like that. Once again, we pass in the command buffer. There we go. And now we need to pass in some values here. You'll notice it's the vertex count, the instance count, the first vertex, and the first instance. Now, all of the vertices that we made were hard-coded into the vertex shader, if you remember. We haven't set up any vertex buffers yet. So since we hard-coded 3 vertices, we're just going to say for the... Sorry, let's bring this back up again. For the vertex count, we have 3, because that's all we made. Then we have the instance count. That's actually not going to matter right here. It's only if you're doing instance rendering. We aren't going to be doing any of that. Instance rendering has to do with when you're trying to render multiple copies of the same object, and it we'll render multiple ones in a single draw call, but we're not going to worry about that right now. So we're just going to do one instance, and then we need the first vertex, which is going to be 0 because we want to start at index 0, and first instance it's 0 as well because we only have the one instance. So that handles everything for the draw call. Now that after completing the draw call, we can end the render pass. So we're going to just do vk cmd end render pass. And just like always, we pass in the command buffer that we are currently using. There we go. And then we can end the command buffer recording, which is going to be if, and it's vk end command buffer does not equal vk success. And for an argument, it just wants the command buffer again. So once again, command buffer I. If it's unsuccessful, we are going to throw std runtime error, and we're just going to say failed to record command buffer. And we're not going to have an else because, once again, this is being done in a for loop. We don't want it to yell at us over and over and over and over, unless something goes wrong. So that's everything we need. And come to think of it, I don't think I used throw in my other runtime errors, so I should have. That was a mistake on my part. Let's go back up to these other two runtime errors. Oh, I actually missed quite a few of them. 3. Okay, good. That looks like all of them now. Okay, so that should be everything for our command buffer. So now it is time to finally draw something. This is going to get a little weird though, because if you remember, I have the game loop running over in tester game, and when I was experimenting with this, it seemed like having it outside of the engine was really kind of messing some things up. So I'm actually going to move the game loop into the Vulkan engine, and we can always move it around again later if that's not working out. So what we're going to do is we're actually going to, in planetvulkan.h, where are the public? Here we go. So we have init Vulkan right here, and right underneath that I'm going to make a void game loop so that we can just call this inside Planet Vulkan. And then over here in the CPP, let's do it, we'll do it right here actually, right up at the top. Right after init Vulkan, we'll do void Planet Vulkan game loop. Alright, and we're pretty much just going to copy what we have in the game loop over here. Copy that, take it over, drop it in here. So we have glfw poll events. Oh, and actually we don't need this mengine here anymore because the window object is actually part of Planet Vulkan, so we're fine. So we've moved our game loop successfully. Now that we have it here, over in tester game we shouldn't be running this game loop. So instead, what we're going to do is we're just going to get rid of the... let me double check this. Yeah, good. So we're going to get rid of the game loop function altogether, because it's not really necessary anymore. And then we're just going to go ahead and call mengine.gameloop. So it's going to initialize Vulkan and then start the game loop. And we don't need any of this anymore. We can just get rid of that entirely. That'll work out nicely. Great. Okay, so let's hop back over here. So after glfw poll events, we're going to want to draw a frame. And we haven't actually written a function for this yet, so we're going to need to make a DrawFrame function. You know, I'm just going to go ahead and call it, even though we haven't made it yet. DrawFrame. Alright, now let's go actually create that function. So we're going to hop back over into the .h. There we go. And right underneath create command buffer, we are going to make a void DrawFrame. Okay, great. So we have that. Let's just grab the whole thing. And we're going to drop down what was the last function we made? It was the createCommandBuffers. So there we are. Just go right underneath createCommandBuffers, and we're going to make DrawFrame. And of course, don't forget to add the scope. I don't know what sculpt is. Speaking problems. Alright, so within the DrawFrame function, we're going to acquire an image from the swap chain, process the command buffer with the image, and then return it to the swap chain to present. Now we want these functions to wait until the previous one completes because it's necessary to render properly. But we can't guarantee that right now. There's no way of doing so. So what we're going to need to do is we're going to need to use semaphores to control that. And if you've never used semaphores before, they're just variables that control access to a common resource in a program. So let's go ahead and get started making those. Now, the good news is that Vulkan actually has semaphores built into it. So what we're going to do is we're going to hop over to the header file, scroll back down, and after the command buffers, we're going to declare two semaphores. So they're both Vulkan objects. They're going to need to have a vDeleter wrapper. So we're going to do vDeleter, and the first one is going to be, well, they're both going to be VK semaphore. There we are. And the first one's going to be the image available semaphore. There we go. And we're just passing in all the usual data, so the logical device, and the delete function, which is a VK destroy semaphore. There we go. And because I'm going to be a little bit lazy here, I'm going to go ahead and just copy and paste that to make the second one, because all the data is the same, it just has a different name. This is going to be the render finished semaphore. Alright, and so the purpose of these two, they're going to be used to determine when a new image is available in the swap chain, and the other one will determine when an image is completed rendering and is ready to present. The name's pretty indicative of what it's going to be doing, but anyways, we're going to need a function to actually create these objects, just like everything else. So we're going to move back up, and after, we'll do it after createCommandBuffers, because DrawFrame's a little bit separate. Put that there, and this is going to be create semaphores. There we go. And once again, just grab it, hop over to the CPP. I'll just drop it right here real quick before we forget. I'm prone to forgetting. Void planet Vulcan, create semaphores, and we do need to call it, so we'll move back up to the top and just drop it right after createCommandBuffers, like so, and now we'll jump back down. So now we can get started creating the semaphores. Now luckily this is pretty easy. All we need to do is call create functions for the semaphores, and they don't take a lot of data either. So watch, we're just going to do if, and we're going to do vk create semaphore, and we pass in logical device. Once again, it needs a createInfo, so we're just going to say semaphoreinfo, and we'll fill that out in a second. And then null pointer for the p-allocator, and then image available semaphore dot replace. Okay, so that's the first one, and we're actually just going to couple the two of these into the same error check. So we're going to say does not equal vk success, or, and let's just drop this down to another line so things are a little prettier. There's going to be another, actually I'm just going to copy and paste things again. It's not the best programming practice, but it does save some time. And the only difference is this is going to be the render finished semaphore. There we go. So that's everything we need to create them. And let's give the brackets for that function. And we're going to do throw std runtime error. And this is failed to create semaphores. and else cout semaphore, quotes help. Semaphores created successfully. And end the line. Wow, EDM. Don't know where I got that from. Okay, cool. So now we need the semaphore info, and like I said, this is really simple to fill out compared to all the other ones we've done. It's a VK semaphore. Wow, I really wish I could spell. VK semaphore create info. There we go. We'll call it semaphore info since we already did. There we go. And all we have to fill out is the S type. If only were always this easy, right? And this is going to be a VK structure type semaphore create info. Perfect. So that will create all the semaphores that we need, and we will be ready to go. Alright, now it is finally time to fill out this DrawFrame function. We're finally going to draw. So first off, what we need to do is acquire an image from the swap chain. So the way we do that is we do VK acquire next image KHR. And we're going to pass in the logical device. Then we need to pass in the swap chain. Then we need a timeout variable. This is going to be how long the program waits for an image before timing out. And we want this to be disabled. So the way we do that is we actually set it to the maximum value of uint64t. So we just do std numeric limits, and we're going to pass in uint64t. And that, and then max, like that. And what that'll do is it will completely disable the timeout. And then we're going to pass in the image available semaphore, because it's expecting, if we look right here, it's expecting a semaphore and a fence. The semaphore we have, the fence we don't. They're both just different kinds of synchronization objects to signal when the image is available. So we have our image available semaphore, and then for the fence, since we don't have one of those, we're just going to pass in a VK null handle. And then we also need an image index, and we're just going to pass in, well, we're going to create a variable for the image index. It's going to be a uint32t. We'll call it image index, and that's just going to get passed in at the end here. That's it's an output variable, so it's going to hold the index of the images after the acquire processes. So we just pass in a reference to image index. There we go. So that's acquiring the image that we need. Now we need to submit the command buffer to the graphics queue. So to do this, we're going to call vkQSubmit, which is kind of similar to a create function. So we're going to put that inside an if statement like always and check whether it's successful. And it's going to be vkQSubmit. There we go. We're going to check whether or not it's equal to vk success. Alright, and we need to pass in, since we're submitting to a queue, it needs it, if we mouse over it here, you can see it needs a queue being passed in, which is going to be our graphics queue. Sorry, not graphics queue, display queue. There we go. Display queue. Then we also need, what's the next one? The submit count, which is just going to be 1 since we're submitting a single command. We need to submit info struct, which we're going to fill out in a moment. So we're just going to go ahead and call that, do a reference to submit info, which is a non-existent variable that we will create. And then we also need a fence, which we aren't using. We're using semaphores, so we can once again just pass in a vk null handle. So that's all we need there. And once again, we'll just throw std runtime error, and we'll say failed to submit draw command buffer. Okay. And now we need to fill out that submit info struct. So first we need to declare it, just right up above. Right there is perfect. And it's going to be a vk submit info, and we need its s type, which is going to be vk structure type submit info. There we go. So next up, we're going to need to fill out data for the wait semaphores. This is going to tell the queue which semaphores to wait on before executing, and which pipeline stages to wait at. There's going to be a couple of different variables to fill out. It's in submit info. We have the p-wait semaphores and the p-wait DST stage mask, and then wait semaphore count is going to show how many semaphores we're waiting on. Both of these are going to expect an array, so before I actually create this variable, I'm going to create the arrays that we're going to pass in. So we need a vk semaphore, and it's an array, so we're going to call it wait semaphores. It's an array, and then just like we did previously, we're only going to put one element in the array, but at least it's now the proper structure. So we're passing in the image available semaphore that we created before. And then we're also going to make a vk pipeline wait stages, I believe. Oh no, I'm sorry. Pipeline stage flags. There we go. And we're going to call it wait stages. And declare it as an array. And this one, it's going to contain just one struct, which is a vk pipeline stage color attachment output bit. There we go. That's the one we want. So what this is doing is it will wait for the image available semaphore, and it's going to wait when it reaches the color attachment stage. So we're going to fill out all that data now. So we have submit info, wait semaphore count is going to be 1 because we only have the image available semaphore. Then submit info p-wait semaphores is going to be wait semaphores. And submit info p-wait DST stage mask is going to be wait stages. There we go. So that handles everything we need for the first semaphore, but the second one, the one that triggers when everything is complete, we need to fill out information for that as well. So we're going to make another vk semaphore. There we go. And this one is going to be signal semaphores. And we're going to set this one equal to the render finished semaphore. So once again, we're making an array for it because it's going to expect an array, but we're only putting in the one element. And we do submit info signal semaphore count is going to be 1 because we only have the 1. And then submit info p signal semaphores, and we're going to pass in signal semaphores. So what that's saying is these are the semaphores that it will These are the semaphores that it will signal when the process is complete. Last up, we're going to need to specify which command buffers to submit. The submit info is going to expect 2 variables. One is the command buffer count, and one is, of course, the pointer to the command buffers that are being passed in. Now, we're going to want to use the command buffer at the current image index of whatever it is that we're processing. So we're just going to go ahead and say submit info command buffer count is going to be 1 because we only have one image that we're processing at the time. And then submit info dot p command buffers is going to be equal to a reference to the command buffers vector at the current image index. just like that. So that handles submitting the commands to the queue, but there's still something we haven't done yet that we should. Let me show you what I'm talking about. We're going to move back to the createRenderPass function, which I know we haven't messed with for a little while. So where is it? This looks like might be the right area. Graphics pipeline, RenderPass, here we go. So in createRenderPass, we have this section for Subpass. Now, multiple subpasses are taking place within a single render pass. The particular one that we have is to handle the layout transition of the images, and there's also undeclared subpasses that happen at the beginning and at the end of the render pass. But the problem is the subpass at the very beginning is trying to deal with an image that doesn't get acquired until the graphics pipeline is already processing. And we need to set up subpass dependencies to wait for the VK pipeline stage color attachment output bit, because without that, there's nothing for the subpass to handle. So what we're going to do is in createRenderPass, we're going to add in a struct for a VK subpass dependency. So right underneath the subpass here, we're going to just add that in. It's a VK subpass dependency, and we'll just call it dependency. Did I spell that right? Yes, I did. Okay. Just like that. Alright, and then we fill out all the data for it. It's just like any other struct. So the first one that we have here is going to be, well, actually we have two of them. There's dependency source subpass, and there's also a dest subpass. So the source subpass is going to be vk subpass external, and that's referring to the undeclared subpasses that are at the beginning and end of the render pass. So because you have the source subpass and then you have the destination subpass, the source always has to come before the destination. So in this case, because I put it as a source subpass, vk subpass external would be referring to the first subpass that takes place before the render pass. And dest subpass, we're just going to pass in a 0. That's the index of the subpass that we created. Since we only have the one, the subpass that's right here, that's what this 0 would be referring to. So we have that. We're also going to need dependency. There's a source stage mask, and for this we're going to pass in vk pipeline stage color attachment output bit to match up with the color attachment that's being referenced by this subpass. And then dependency source access mask, which is going to be 0 once again. Then we also need a dependency dest stage mask. Oh, DST. There we go. Dest stage mask. That's going to be vk pipeline stage color attachment output bit again. Type this whole thing out. There we go. And there's also dependency dest access mask, which is going to be vk access color attachment read bit, and we're also going to do vk access color attachment write bit, just like that. So what this is doing is preventing the reading and writing of the color attachment stage from processing until the color attachment output has been retrieved. So that way we won't end up with it trying to process something that isn't there. So now that we created this dependency, we need to add that into the render pass info. So down here, right underneath the subpass that we declared in the render pass create info, we're also going to add in render pass info dot dependency count, which we left out before. And we're just going to declare 1 because we only have the one dependency up here. And then render pass info p dependencies, and we're just going to pass in a reference to the dependency struct that we created. Now we can get back to finishing up our draw function. We're almost there. Let's just get back down there again. Here we go, DrawFrame. So we are right after the if vkq submit. So we need to receive the output of that submission and then present it. So the way that we present it is by calling vkq present khr. And all you have to pass in is the graphics queue. Nope, sorry. Display queue. There we go. That's forgetting my own names. Display queue, and then you also need a vk present info khr struct, which we haven't created yet. So I'm just going to go ahead and put one here. Just present info, and let's create one right here. So it's going to be a vk present info khr. Call it present info. There we go. And we're going to fill out all the data again. So present info.type, and that's going to be equal to a vk structure type present info khr. So vk structure type present. There it is. Great. Fill things out for me. And we also need the semaphores. So we're going to go ahead. There's a present info wait semaphore count, and we're going to be waiting on one semaphore. And we need to say what that semaphore is. So there's, of course, p wait semaphores. And we're just going to pass in the signal semaphore array, which is only one semaphore. It is that render finish semaphore right here. So it's going to wait on that one to move on. And then we also need to pass in the data for which swap chains to present to and which image index to target. So this is going to be another one of those situations where it expects an array, even though we only have one thing to pass in. So we're going to do present info swap chain count. Like I said, there's only one. And it's going to want, it's right here, it's present info p swap chains. And this is where we would pass in an array of all the swap chains that we're using, but we don't have an array. So right here we're just going to declare vk swap chain khr, call it swap chains, declare it as an array, and we're just going to put our swap chain right there in the array, and then pass in a reference to swap chains right here. And then we also need present info dot p image indices, and for that we're just going to pass in a reference to the image index that we filled out right up top, right here. That was the output of the acquire next image khr. So now we have all the functions that we need to draw a frame. So at this point we could run everything, and in theory it should render something for us. There's still just a couple tiny things that we haven't done yet that we really should, just to make sure that things are running properly. So let's pop back up to the game loop at the top here. So right now we have this while loop that's running for our game loop, and it's pulling events, drawing the frame, and it's doing this while the window is open. Now, if the window gets closed, we really should clean up that window. It should be destroyed. So since glfw is our library, we're just going to call glfw destroy window, and it'll handle everything we need for that. And we just need to pass in the window that we're destroying. So we pass in window object.window. Alright, so that'll clean up the window for us. There's one other problem, though. Right now, if we were to close the process, it's possible that it would destroy the window, but it would still be running render processes. So to prevent that, right here, just above it, we're going to put in a vk device wait idle, which is going to wait until a particular device is no longer processing something. And we're going to go ahead and pass in the logical device. So until the logical device completes processing, it will wait here to destroy the window. So that should keep us from running into any unexpected errors. So now that we have that, we should be done. We should be able to finally get something on screen. Let's give this a try. So we're just going to go ahead and run the program, let it build, And if we succeeded, we should have a nice rainbow triangle. It's the first time we get something out of 11 videos. It's pretty exciting. Come on. Give it just a moment. And let's see what we get. And there it is. Oh, that feels great. So there is finally something on screen. We have a nice rainbow triangle. That's everything that we hard-coded in our shaders, if you remember. The vertex shader had all the vertices for the triangle. The fragment shader had all the colors. And if you look over here in our little log, you can see everything was created. There's the graphics pipeline, the frame buffers, the command pool, command buffers, and semaphores. So now we have it. You can go and show this off to people and tell them how hard you worked to get this triangle, and they'll give you strange looks. But that's just kind of how things go with programming. Anyway, so that's all for this video. In the next one, I'm going to make a few more touch-ups to the way the engine behaves, and then we can get started creating the vertex buffers so that we can control the data that we pass into the engine. Shortly after that, I think I'm going to go through a series of refactoring this code, because I'm sure some of you have noticed it's gotten rather messy. It's all mainly in this Planet Vulkan script, and I'd kind of like to break it up a bit more. So I want to finish off everything within the pipeline first so that we have that vertex buffer, and then after that I'll probably refactor things rather considerably. So anyways, thanks for sticking with the videos this far. As always, if you have any questions or comments, feel free to leave them in the comments section down below. And if you'd like updates on when I release another one, just go ahead and hit the subscribe button. Thanks for watching, guys.